Okay, good afternoon, everybody. I'm Rosa Badia from the Barcelona Supercomputing Center, and I will be sharing this webinar today. We have today Lizy John, who is a professor at Research Foundation Chair in Engineering at the University of Texas at Austin. Her research interests include computer architecture, performance evaluation, memory systems, reconfigurable architectures, and hardware architecture for emerging workloads. She has received many awards, including the John J. King Professional Engineering Achievement Award and the Pennsylvania State University Outstanding Engineering Alumnus Award. And also she's an IEEE Fellow, ACM Fellow, AAAS Fellow, and Fellow of the National Academy of Inventors. So today, and also she's an author of many articles and books and book chapters. She will be presenting today nanoML, pushing the limits of edge and edge AI with weightless neural networks. So please welcome Lizy with me. Please feel free to start whenever you want.
Thank you so much for the generous introduction, and thank you for this opportunity to be speaking in this webinar series. I was in Barcelona in January, but I almost feel like I'm there, although I'm not able to see the audience. But so the topic I have today is Edge AI, and I thought a little bit about it, whether, with supercomputing, is this the right topic? But then I thought when I was there at the HiPEAC event in January, there was a lot of discussion about swarm intelligence. And so Edge AI and pervasive intelligence seems to be very relevant and for HiPEAC and the research initiative. So I thought I will use this topic. So it's Edge AI with a different kind of neural networks than the ones you usually hear about. And before going into the topic, I would like to give thanks to the University of Texas, which has given me the opportunity to work with people like John Goodenough, who was the 2019 Nobel Prize winner for chemistry, but he was my colleague in my department. He invented lithium rechargeable batteries. And Professor Bob Metcalf, who is the Ethernet guru, and he got the 2023 Turing Award, and he's also my colleague. And the students, the graduate students who do the hard work that I can talk about. So basically, AI is everywhere, but the carbon footprint of AI is huge. The popular types of neural networks, deep neural networks, they contain billions of weights and trillions of multiplications and additions to do the job. These networks require significant amount of compute and energy. But when you think about how they actually perform, they do the intelligence using extensive digital simulations to model analog brain processes, and largely based on the multiply-add neuron, the McCullough-Pitts threshold logic neuron, which basically has coefficients on each of those arcs. The inputs are multiplied by the coefficients, the products are added, and depending on the activation function and the threshold, if the sum is above the threshold, it fires or it is activated. So this neuron model has been successful with a large amount of computing and with the availability of GPUs and large data set. From 2012, there has been a significant increase in capability utilizing this neuron model. But there are also reasons to look for alternate neuron models. Bengio, and in the 2017 ISCA talk, they mentioned the brain is about 500,000 times more energy efficient than an NVIDIA P100 GPU. And this is years ago. My newest graduate student who went to NVIDIA told me, yeah, don't use that number. GPUs are better. I said, okay, give me a number. And he gave me 13,000. I said, that's fine. That still gives us enough reason to think of more energy efficient neuron models. So the models built on the multiply add or the McCullough-Pitts neuron, they are very power hungry. And there is also another thought, human brain contains 100 billion, approximately 100 billion neurons. They switch thousands of times, 1,000 times per second. Modern chips contain roughly similar number of transistors, about or higher than 100 billion transistors. And they switch much faster, 10 billion times per second. Yet the chip is nowhere as intelligent or energy efficient as human, though equal number of transistors or neurons or more transistors than the neurons. So in comparison to the McCullough-Pitts neuron model, where all the synaptic connections directly terminate at the neuron soma, in the brain, apparently, the vast majority of synapses terminate on the neuron's dendritic tree. So if in the most noticeable morphological structure in the brain is the dendritic tree, and dendritic computing is maybe an alternative to the integrate and fire McCullough-Pitts neuron model. So dendritic computing, there are thoughts on doing it many times. What I have here is purely digital, and it is based on the RAM neuron. And there has been early works on the RAM neuron, like the 1959 RAM neuron work, whether you have here a 4-entry RAM, and so 2 address bits and 1 data bit, and you are using the lookup table as a model to capture intelligence or information and be intelligent. This was proposed for pattern recognition and reading. There have been a little bit more written about the dendritic decoding and synaptic function, and this is the first page from that chapter from that book. But essentially, there is discussion in the way of dendritic decoding, which has excitatory and inhibitory functions and a decoding. So if you have a dendritic tree and each E is an excitatory function, I is the inhibitory function, so the signal reaches here or not depending on the I values. And then there is basically, so anything at the towards the root has veto power, because even if all these things came, but depending on what happens here, or if this is inhibited, none of this are going to reach here. So there are neuroscience works on the dendritic way. But now what are we doing here in the lookup table or memory-based neuron? One, from the digital design point of view, a lookup table with 2 input variables, which has 4 locations, can contain any one of 16 different functions. The 16 different, so 2 to the 2 to the 2, 2 to the 4, or 16 different functions. These are the 16 different functions, logic functions, that are possible for 2 input variables or 2 input LUTs. So all function values are zeros, to all function values are 1, and every combination in between, because there are 4 input combinations, there are 2 to the 4 combinations of possibilities for the function. So a lookup table can have any one of these functions, and if we have a way to train and learn the correct function that should go in a lookup table, that's another way to have intelligence, versus the multiply accumulate neuron model, where we derive the coefficients during training and multiply during inference. So an alternate approach. So there are some machines built in the 1980s which have this principle, which used lookup tables. the popular one is called the Wizard, Wilkie Stoneham Alexander recognition device from Imperial UK. And essentially, the input image or the input retina is randomly mapped to different pixels, are randomly mapped to different RAMs as shown by these arcs. And during the training phase, you look at the images and train each of the RAMs using, so let's say we are training for letter H and there are these 3 H's in the training set, and you only look at one input one time. There are no epochs of training, just one epoch or one time training. So you could call it one-shot learning. Some people call it snapshot learning because you are learning from each of those examples and you only use it one time. And the inputs get mapped to the certain RAMs, and depending on whether the pixel was a 0 or a 1, the RAM entries are modified. And during inference phase, you are taking whatever is the new image and you are checking with that same mapping, you are finding out whether this is the letter H. Now, there have been this whole thing, the 6 RAMs shown here to detect H is called a discriminator. And if you have 26 letters or 10 numbers, so there will be that many classes in your neural network, and there will be one discriminator per class. There are some techniques that are used called a unary encoding to binarize the input called thermometer encoding. There are also techniques called bleaching that makes, if you have many inputs and some inputs are seen a lot and some are seen very rarely, to give different weights to how you modify things. So essentially, lookup tables that contain the information. Now, if you have one huge lookup table to capture the information or learn from the information, that table is going to be very big because there are so many features and so many inputs. So instead of one big table, having small tables is one technique to make it practical to learn with less memory. So this is a discriminator. Here 4 RAM nodes are shown and the contents of the RAM node. This whole thing is one discriminator. If I have MNIST or 10 digits, I have 10 discriminators for each of them. Now, VC dimension is a metric that can be used to tell the complexity of the knowledge a classifier can represent. And the VC dimension for lookup table based neurons is basically much higher than equivalent DNN neurons with the same number of parameters. So if a DNN neurons with n inputs, the VC dimension is n plus 1, whereas the lookup table, it is 2 to the n. And as a simple example, let's say we want a 2-input XOR function. A DNN will need 3 neurons and 9 parameters, whereas the weightless neural networks based on the lookup table neuron will need only 1 neuron and 4 parameters, the 4 entries in that 2-input RAM. And lookup table neurons are nonlinear, and there is also from neuroscience information or thought science that says biological neurons are nonlinear. And so arithmetic versus logic. The Mcculloch's neuron uses arithmetic functions. Here we are using logic functions and memory lookup table nodes. Now, there are many challenges to make this to work. Memory required can be large depending on the amount of features that are to be used. And most of the memory locations will be 0. So we can actually use good hashing methods and filtering techniques to reduce the size of the memory. The biggest challenge in the lookup table based neuron or the weightless neuron is how to do the training. And the training is, so far what I explained is a one-shot training one time. But conventional DNNs, the reason for the good accuracy is the feedback-based training, so gradient-based improvement in the weights. Now, the basic weightless neural network historically never had a method to improve the accuracy of the lookup table contents based on your own mistakes. So it's only trained one time. So how do you design gradient-based update rules for binary values in a lookup table? That's very challenging. Binary neural networks face some of this because the derivative of the unit steps 0 to 1 or 1 to 0, it's very unruly. It's 0 almost everywhere, but right at the place it's infinite, and there is no way to back propagate through this. But we want to have a method to learn and have a gradient based on which we can improve the accuracy of a weightless neural network. So Bloom Wizard, this helps to reduce the size of the RAM because it's a good hashing method and you only hold relevant values or that has been used in the past. We even without the feedback, just with the one-time training, we could actually get a lot of improvement in comparison to baseline CNN models, MLP models, as well as just a multi-layer perceptron model. CNNs are very big. So with respect to CNNs, we are actually like 0.1, 0.01, something like that. So just to be more fair and utilizing multi-layer perceptron models, we can get 90% or so reduction in latency, energy, etc. Now, but the accuracy here, it was the comparison was done with ISO accuracy DNNs. But DNNs are capable of getting better accuracy. So this particular one was for MNIST, it was 94.2, whereas DNNs can get 99% accuracy. So how do you improve the accuracy of weightless neural networks? So multi-pass learning can improve the accuracy. And so recently, or in the last 7 years or something like that, binary neural networks have used a straight through estimator, essentially where the unit step is instead of using considering the gradient as infinite, the gradient is considered to be 1. So that is a proxy gradient with which BNNs or binary neural networks have done training. So we utilize the same principle. We also during training keep the contents not binary but have 8-bit or some fractions, which allow you to basically have more accuracy. Post training it's binary, but during training it's a little bit more accurate than binary. So during 22-23, we have been able to reduce the error for edge applications, and this is keyword spotting. This is anomaly detection data set called TOI-ATMOS, and this is the digit detection MNIST. The accuracy, the errors have reduced from 8% down to 1%. And in KWS, the errors have reduced from 70% down to 30%, and in the anomaly detection from 45 down to 12. So quite some improvement without increasing the model size. So the model size actually has reduced because we have the Bloom filters and other techniques to reduce the model size. And most recent work, 2020, covering up to 2024, the accuracy is improving or size is reducing. The most recent one is 2024 ICML conference, our work called Differentiable Weightless Neural Networks. So I'll go a little bit into that. This is the newest work, Differentiable Weightless Neural Network. So this is about training. Ordinarily, we couldn't differentiate a lookup table and improve the contents of the lookup table to get better accuracy. And because there is no usable gradient for a lookup table. And so there is quite some math about what we did for the lookup table approximate differentiation, because lookup tables are discrete and a polynomial function and finite differences and steepest descent and extended finite difference. So we considered a few mathematical methodologies to come up with approximate differentials or derivatives for a lookup table. And ultimately, so I'm not going to spend too much time on the math, but finally, with the extended finite difference technique, by which you take an entry, and if the entry was to switch to the next one or the previous one, so changes of one or change towards all possible directions but weighted towards it. So this function was the one that gave us the best accuracy, the extended finite difference. So this extended finite difference is used to learn the lookup table contents, as well as now we started more layers of lookup table, 2 or 3. We didn't use more than 3. We could get the accuracy, a good improvement in accuracy. So 2 or 3 layers. And the connections between the lookup tables are also learned. The connections from the input features to which lookup table they should be connected, it's early on we were using a random mapping. Now the mapping is also learned. So the learnable mapping of the inputs to the first layer of lookup table, learnable mapping of the connections from lookup table layer to layer, and at the end, when you have different in a discriminator, you will add up all the contents to see what is the response for that class and what is the response for another class. So there is a summation or pop count or population count at the end of each discriminator, and that is also learned, because adding a ton of binary values, that hardware can be pretty big. So that's also learned. So learnable mapping, learnable reduction with using extended finite difference has helped to improve the accuracy of the weightless neural networks. And so during training, we do passes similar to BNN, and Xilinx has a tool called, the FPGA company, they have a tool called Fin. We use some of those similar training techniques but use extended finite difference. During inference, so there are no weights. The connections are all fixed, and inside the lookup table, there are zeros and ones. Some people ask me, are in the zeros and ones like weights? There is no multiplication. We usually call weights because we weight the input by multiplying the weight with the input. There is no more multiplication. And so that's why historically this has been called weightless neural networks. I am perfectly comfortable calling it the LUT neuron-based, lookup table-based neuron. There are some other works and some recently. This is from Xilinx, the FPGA company. They call it logic nets. And PolyLUT and NeuralLUT are from Imperial College. And so these are all methods where a neural network is learned, and post-training, it is put into lookup tables. Similarly, there have been also some works where there was a paper called multiplication without multiplication, because the multiplication is only with certain weights or certain things. So you can have a pre-computed lookup table, and based on the pre-computed lookup table, an approximate multiplication is performed without multiplication, because each multiplication becomes a lookup. So there have been other works that also found the amount of multiplications we do in DNNs is too much. We somehow want to make it more efficient, but the core difference with the weightless neural networks from all of these other works is that we are not converting a multiplication into a lookup. We are learning the lookup tables. So it is a lot more efficient because the intelligence is acquired or learned with the lookup table rather than learned by an arithmetic function and converted to a lookup table. So we evaluated the differentiable weightless neural networks on 4 different scenarios in an FPGA, the field programmable gate array, which inherently fits the weightless neural networks because the FPGAs contain small lookup tables. FPGAs, the CLB or the programmable logic block in an FPGA, nowadays in both the Xilinx as well as the Altera or Intel FPGAs are both 6-input lookup tables. So we can prototype our neural networks very easily in an FPGA. But we could also do it as a purely software model in a microcontroller for the edge. We could make tiny ASICs. So we have done all 3 of those. And we also noticed that the weightless neural network is particularly suitable for tabular data, where data is in tables. So when you convert a weightless neural network model into an FPGA lookup table, currently the lookup tables have 6 inputs. So we basically train with 6 input lookup tables and put into the FPGA. And we are comparing with FIN, the industry standard from AMD Xilinx, with binary neural networks, which is a lot more efficient than full precision DNNs. And so we use the FIN, the best binary neural networks available for comparison. We also, in the last 4 years, we have done, so some of our own work from before are compared against the newest work, the differentiable weightless neural networks. We also compare the best other work that, or interesting other work that we came across called the Diff Logic Net. It was a NeurIPS 2022 paper. They think of neurons as 2-input logic gates. And so if you make neurons and each logic gate, they are going to learn, like I showed before, there are 16 logic functions for 2 inputs. So here they are trying to estimate the probability for each of those functions. And if they see that this neuron or this gate XOR, there is a 78% probability, and there is a 3% probability for AND and 7% probability for NAND, they make it an XOR. They do that for every gate. So after training, each gate assumes its most likely function, and that is the diff logic net. So a comparison, FIN is the binary neural network from AMD Xilinx. Ulean is our own previous generation of weightless neural network. Diff Logic Net is Felix Peterson, this one, the one we just had, that's Diff Logic Net. And DWN is the newest weightless neural networks that we have. We could do it for 2-input lookup tables, and we have done it for 6-input lookup tables. 6 because that is what is in the AMD Xilinx. 2 because it allows us to compare with the Diff Logic Net, which uses 2-input gates. So when you look at this, accuracy for this keyword spotting data set, and we have the best accuracy with the 6-input lookup tables. Parameter size is smallest for the 2-input lookup table, but even the 6-input is less than all of the other cases. The latency. Now, the biggest thing about latency is we have 1 or 2 or 3 small, not many layers. So our latency it's very fast. In a binary neural network, often there are many layers. It's just binary, but many layers, deep networks. and the latency is much higher, 7,700 here as opposed to 200 for us. The throughput, we can do 10.5 million inferences per second. The binary one is 0.67. Energy, we are at 42 nanojoules per inference versus in the binary 5,700 nanojoules per inference. So essentially we can get nanoseconds of latency and nanojoules per inference for energy. Now, another edge dataset, human activity recognition, the HAR dataset. These are some of the prior works, not Weightless, and CNNs and other ways of doing handling this dataset. We have comparable accuracy and comparable F1 score. The model size is tiny for us, 19 kilobytes, 39 kilobytes, as opposed to megabytes for them. And flops, the amount of compute, we don't do any multiplications. This is the floating point operations needed in them. And when they take millijoules, we take nanojoules. So very reduced energy and latency and model size. So a few more data sets and the same comparison in FPGA with binary neural networks and DiffLogic-NAND. And the differentiable weightless neural networks are shown to exhibit superiority in latency and throughput and energy. Now, for tabular data, there are also other kinds of networks. Google's TabNet or AutoGluon has XGBoost, CatBoost, many other ways of doing inference on tabular dataset. So we are comparing against them. These data sets are chosen because they have been used in some other prior work, so we do exactly the same things. And when you compare, we are the best in 5 cases in terms of accuracy, and every other column has some, maybe, some columns the best is here or here. But when you look at the average and you look, if you are the best, the average rank for us is 2.5. And these are the average ranks for the other tabular techniques. And our L1 score is 0.005 and better than everybody else's L1 score. So on an average, we are still pretty good, even in comparison to other tabular techniques. This is graphical illustration of the same data, so I'm just going to go through it quickly. The polyLUT and neural LUT, which are from the Imperial College 2023 and 24. So we use some of the data sets that they have also used the jet substructure classification from particle physics data set. And so essentially we are able to appear to be, we compare favorably against polyLUT and neural LUT as well. Now, coming up with tiny ASICs, ultra low cost chips that can be used in, intelligence, pervasive intelligence on the edge in IoTs and tiny devices. So there was a paper last year from UK in Nature, and they have an evolutionary algorithm to come up with a tiny classifier for the data sets that I had on the previous page. These are the data sets they also use. They can say a budget for gates. Okay, I have 300 NAND gates. Give me a neural networks connecting 300 NAND gates, and that's the algorithm. That was the contribution in this paper. And these are the accuracies they get. DiffLogic-NAND that I compared previously also, they can also use 300 NAND gates to come up with a neural network. This is the count and this is the accuracy of what can be achieved with that. In comparison, the weightless neural network, the differentiable weightless neural networks, we can get these accuracies with the NAND gate count shown here. The fewer NAND gates than either of these two columns and better accuracy than either of these two columns. So for tiny edge problems and tabular data, we basically, the differentiable neural networks are attractive for low area, low energy, and still yields high accuracy. And so we have been thinking about how to, what are some use cases where this could be used. So medical, this is cardiac. One of my colleagues has an e-tattoo. This is Professor Nancy Liu from mechanical engineering. She basically has this medical research where a credit card sized e-tattoo can be stick on your skin. It has a battery, it has the sensors, and it has a microcontroller, and it can basically do continuous monitoring of the heart health. And so what is in it is shown here. It has wires that stretch, so it is flexible, it is not rigid, it can be stuck, and these wires will stretch and not break. That is one of the key parts of that e-tattoo. And currently they use the microcontroller to get these signals and send them using the Bluetooth to a phone and do the processing in the phone. So ECG, SEG, PPG, many of the cardiac health signals can be measured, and they send it to the phone and do the processing. So they use neural networks on the phone or in a computer. So what we are trying to do right now is, in the microcontroller on this e-tattoo, we can put this tiny neural network. A random forest-based or CNN, some other neural network will not fit into this tiny tiny microcontroller here. But because we have a neural network that is really tiny, so we have already done this. We are collaborating with them, and we have created the small neural networks to be measuring and detecting a cardiac volume or stroke volume for the heart using and without using the phone. Just do it inside the tattoo itself. So the advantage of that is now the battery would drain in 2 hours, but if we do not have to transmit to the phone every signal and you're doing the neural network computation right here, the battery may last 2 days. So that is the difference because it's energy saving. Another collaborative project, this one is with Pragmatic in UK. Emre Ozer, who was the keynote speaker at the HiPEAC conference in January. So we basically created, so they have a plastic substrate. The plastic substrate, it's not the 22 nanometer or 15 nanometer or anything. They are at like 600 nanometers. They're improving, but at the time we were doing this at 600 nanometers. And you cannot integrate millions of transistors on this plastic technology. You can integrate 10 or 15,000 transistors. Most neural networks, convolutional neural networks or others, will not fit into 15,000 gates. We were able to create an arrhythmia detector in less than 3,000 gates. So we design this weightless neural network for arrhythmia detection and put it into the flexible IC offered by Pragmatic. And this is the fabricated one, and it was tested. It doesn't need packaging. it is tested using this prop tester and basically shown to be working. And there is this paper last year in the Flexible Electronics Conference in September last year. So the weightless neural network is an attractive, it's a radical departure from other neural networks. We have even one layer of lookup table does a lot, but with the 2 or 3 layers, sometimes for some problems, you get much better accuracies. The mapping of the features to the lookup table, as well as the interconnection between the tables, are all learned in this training process, which uses extended finite difference. And they are small, they are fast, efficient, and over fully connected binary neural networks, it is still large improvements. And it is the top performer versus other tabular models. And we can easily put into FPGA because there are lookup tables, but we can also put into software models in tiny microcontrollers, or we can create tiny ASICs. Essentially, this gives multiple applications or possibilities for edge and low power devices, anomaly detection, high throughput particle classification, healthcare in wearables, as in the examples I showed. And of course, the success so far has been limited to edge problems and small data sets. Expanding lookup table-based neural networks to fully to convolutional problems and transformers, language models, that is ongoing work. The challenge with the advantage of convolutional models, they are positioned because you are convolving over all the images, you are basically position invariant, whereas in ours we have one mapping from some pixel, and we do not do too well with complex images. So, but we are working on weightless technologies for accomplishing the same thing. Similarly, for transformers, we have found ways to make some improvements, but fully all layers of the transformer, making it weightless, of course, a lot more work is done. So, very encouraged and excited about what we have seen on the edge and for small scale problems, and trying to incorporate or trying to make adjustments and modifications for convolutional and language problems. So I think that's it. And so thank you, and please ask me questions. And this QR code can take you to the ICML paper that describes even more. So, okay. All
Thank you
right.
very much. I was capturing the QR. Sorry.
Okay, it's right there. Yeah.
Very good. Thank you very much for the presentation. We have many questions actually. You have raised a
It's
lot
in
of
the
interest.
chat. Yeah,
Yeah, I can read it for you if you want.
Okay, let me, yeah, I see the QA. Okay.
They are in the Q&A, but I can read them for you if you want.
No, I can see it.
Okay.
So Eduardo asking, going back a bit, could you develop more on why the gradient-based update phase is a big challenge in the field? Okay. So gradients, practically in the DNNs, we have seen that they help a lot. But the challenge for binary neural networks as well as the weightless neural networks is the lookup table contents are zeros and ones. So let us say we train, then we do an inference, and we see we are wrong. When we are wrong, 0 can become a 1 or 1 can become a 0. But because there is no in-between value, we will always have the last value trained. There is no way to know if 99 times it should have been 1, but the last one was going down to 0, we'll have a 0 there. because all you can do is flip. There is nothing in between. So instead of treating that gradient as infinitely to the positive direction or infinitely to the negative direction, Xilinx AMD, the Fin2, they came up with the, they use the straight through estimator and making a proxy of +1 and a -1, right? But even that is problematic. And so in our first generation 2023 paper, what we did was we used many bits. So for each update, we will go from 0 to 0.1. Then if there is another one, 0.1 to 0.2, 0.3. And at the end of training, if it is 0.7 or 8 or 9, above 0.5, we make it a 1. If it's below 0.5, we make it a 0. That did some benefit. But it is still not enough because you are training each of the entry by itself. The whole lookup table has a function. That function itself, if we could differentiate and find out what should have been the other function that should have been really in the table, it really helps. Otherwise, we are doing one at a time. So the improvement in the differentiable weightless neural network is to treat it as a function and to decide which function you want to go to. So the challenge is because you only have zeros and ones and of the infinite differential at the point. That is why the challenge. Okay. Could you also comment on the lookup table access overhead? In other words, the overhead of memory reads. Yes, the lookup table access has an overhead, but it's lot less. It is one read, right? In a conventional DNN, we have to read the weight, we have to perform the multiplication, and we have to write the product. So compared to the DNN, we just have one read. So you have multiple reads in a DNN, so it's fewer reads. The lookup tables are actually tinier structures as opposed to the big SRAM or big buffers that hold the DNN weights, DRAM and SRAM and so on. These are tinier structures, so the access energy is also less. So it's only, yes, there is a read, but fewer reads and less expensive reads. Can you explain a little bit deeper the lookup tables? Let me see whether I can go to a slide and do that. Okay. You are seeing the slide with the lookup tables, right? I don't know.
Yes.
Yeah.
Sorry.
Okay. Yeah. So a lookup table is just a small memory structure. 2 inputs, 2 to the 2 or 4 locations. So these are the inputs 0, 0, 0, 1, 1, 0, and 1, 1. So there are 4 values in the lookup table. So the lookup table or that memory structure can contain any one of these 16 rows. It may be containing all zeros, or it may be containing zeros in 3 locations and a 1 in the last location, or it may be containing all ones. So these are the 16 combinations, permutations and combinations of things the lookup table can contain. And depending on what the input is, you will be reading out that particular column. But the function captured by the lookup table is any one of these 16 functions. So a lookup table is nothing but a small memory, 2 inputs or 6 inputs in our experiments, but it can be any number of inputs. The power of the lookup table is its high expressiveness, because a 2-input lookup table can express any one of these 16 different functions. Some of these functions are very commonly recognized, like ANDs and NANDs and exclusive OR and things like that. Some of the functions may not make too much sense, but basically 16 different functions, or a 2-input lookup table with 4 bits of memory can express any one of these 16 functions. Now, when 2 changes to 3, it is 2 to the 2 to the 3 or 2 to the 2 to the 2 to the 8, which is 256 functions. So if we have a 3-input lookup table with 8 entries, it's heavily expressive, being able to capture any one of 256 different functions. So this is why this is fundamentally different from DNNs, where we are multiplying the input with the weight and summing it up. And lots of multiplications. Here it's a logic function as opposed to an arithmetic function, and it is less wide. So, and it is very expressive. And if we had a way to connect a whole bunch of lookup tables and train the right function, which among these 16, or if 3 inputs you have 256, or in the Xilinx FPGA right now, 6 inputs, 2 to the 2 to the 6. It's a huge number because 2 to the 6 is 64. 2 to the 64 is a quintillion, 18 quintillion or something, some large number. We don't need that many functions possibly, but if we can identify, and it is a challenge to identify which is the right function among these 256 or a quintillion functions, that is the challenge. But if we could identify the right function, we have a way to come to our inference without performing trillions of multiplications. Imagine, why are we having to do trillions of multiplications to predict the next word in a language model? Maybe there is a, 30 years or 40 years ago, the rule-based AI, where it was all logic-based programming, it was much more efficient, but you only reached up to a certain point. So maybe there is something in between we can have by learning these logic functions and having layers of them. And you don't have to think and come up with the logic, but you can learn the logic. And if we can come up with that kind of AI where the network learns the logic function, and if it can be accurate enough for many real-world problems, we probably have a much more energy efficient and sustainable AI ML paradigm than, currently we are all excited because all the large language models, generative AI, everything works. Even though it's doing trillions of multiplications, it's working, and which is exciting. However, maybe there is a possibility to do something without spending that much energy. Okay.
Okay, Lizy, we are about to be up to the hour.
Okay.
Sorry for cutting you, but
Yeah.
maybe you can try to be.
Yeah, I can type some answers for these if you want, or would it be possible to compare these machines with settled machines and SNNs? Yeah, we haven't done it yet. We have, that's something to do for the future. Is the approach applicable with all kinds of neural net, or are there layers that is incompatible? We currently don't have anything for attention. We are working in attention layers in large language models. How do you decide on the size of the networks? We have a training methodology which plays with some of it, and once so it's part of the training methodology. What are the disadvantages of these models? Right now, it is the lower accuracy for bigger data sets and more complex images. Also, right now, we cannot train bit-based things so efficiently on GPUs. GPUs work with larger data, but bits, if we want to train, it's kind of slow. Not slower than DNNs, but slower than it could be. Can be described as a LUT? Yes. Yes, you can describe these as LUT-based multiplication-free networks. Yes, you can do that. All right. Thank you.
Okay,
I guess I
thank you
quickly
very
went over
much.
the rest of the questions. Yeah.
No, they were good questions because people is interested. So this is excellent. Okay, so I would like to thank Lizy again for the great talk. It's a very, very interesting topic. I think energy, of course, is very important. Also, the fact that you can develop these small, very tiny models that can be deployed in the continuum in edge devices, and because this is also the topic of the project now, the digital continuum. So really very, very up to the point for the project. So again, thank you to everybody for attending the webinar, and looking forward to meet you again soon.